Turning to the second integral, we are looking at the integral from 1 to 9 of 1 over the cubic root of x minus 9. Again, the first thing is to look at whether this function has discontinuities in the interval from 1 to 9. While we have x minus 9 to the power 1/3, this is going to be discontinuous only when x is equal to 9, which is precisely the right-hand point of the interval of integration in this case. So we have a discontinuity at 9, and that means that our integral is by definition the limit as t is approaching 9 from the left of the integral from 1 to t of dx over cubic root of x minus 9. We can rewrite that as x minus 9 to the power negative 1/3. Because t is less than 9, this function x minus 9 to the negative 1/3 is continuous on the interval 1t, and therefore, to calculate it, we only need to find an antiderivative using the fundamental theorem of calculus. And of course, an antiderivative of x minus 9 to the negative 1/3 is x minus 9 to the negative 1/3 plus 1, that's 2/3, divided by 2/3. So we evaluate that between 1 and t, and the value at t is of course 3/2 of t minus 9 to the 2/3. And the value at 1 is 3/2 of 1 minus 9 negative 8 to the 2/3, which is the same as 8 to the 2/3. And 8 to the 2/3 is really 8 to the 1/3, which is 2 that you square, which gives you 4. When you multiply by 3/2, you get 6. So you have this limit of 3/2 t minus 9 to the 2/3 minus 6. Now if we look at the limit when t is approaching 9, t minus 9 is approaching 0, so 0 to the 2/3 is approaching 0, and that means that the limit is simply negative 6. So in this case, our integral is convergent, and its value is negative 6. In the third case, we have the integral from 0 to 4 of 1 over x squared plus x minus 6. As usual, the first problem is to find the discontinuities of the function. Because x squared plus x minus 6 factors as x minus 2x plus 3, and the discontinuities of this rational function that we are trying to integrate are going to be the zeros of the denominator, we have for the discontinuities of the function 2 and negative 3. The only one that is in the interval of integration is 2. So our function is discontinuous at 2, and that means that our integral from 0 to 4 of that function should be understood as the sum of the integral from 0 to 2 and the integral of 2 to 4, where we have convergence if both integrals are convergent and have a value, and divergent if at least one of these is divergent. So let's look at the first one, the integral from 0 to 2. It is itself an improper integral. Improper because we have a discontinuity at the right-hand point of the interval of integration at 2. So by definition it is a limit as t is approaching 2 from the left of the integral from 0 to t of the function. And the function is continuous now on the interval 0t because t is less than 2, so there's no discontinuity on that interval. That means that on that interval we can use the fundamental theorem of calculus, and we need to find an antiderivative. We are integrating a rational function, so we know what to do. We use partial fractions. We factor the bottom, it's x minus 2x plus 3. These are non-repeated linear factors, so we know that the form of the decomposition into partial fractions is just a over x minus 2 plus b over x plus 3, and in that case we can use the n-cover method to find the coefficients a and b. For instance, to find a, we can multiply everything by x minus 2 and then plug x equal 2. In that case, we have this situation where a is equal to the value at x equal 2 of what we have on the left-hand side, so that's 1/5. Similarly, to find b, we multiply everything by x plus 3 and set x equal negative 3. So b is going to be the value of the left-hand side when x is negative 3, and that gives us negative 1/5. So b is negative 1/5. So that means that we can replace 1 over x squared plus x minus 6 by 1/5 of 1 over x minus 2 minus 1 over x plus 3. So this is what we are integrating. And now we can integrate that because we know antiderivatives. An antiderivative of 1 over x minus 2 on that interval is natural log of absolute value of x minus 2. And similarly, an antiderivative of 1 over x plus 3 is natural log of absolute value of x plus 3. We evaluate this between 0 and t, and so we obtain this expression, the limit as t is approaching 2 from the left of 1/5 of natural log of t minus 2 minus natural log of t plus 3 minus log of 2 plus log of 3. Now what happens when t is approaching 2? For natural log of t plus 3 it's not a problem, it's going to approach natural log of 5. But for this term we have a problem because as t is approaching 2, t minus 2 in absolute value is approaching 0 from the right, and natural log has a limit as at 0 from the right, that is negative infinity. So this term is going to go to negative infinity, and as a result the limit of this expression is negative infinity. That means that the interval from 0 to 2 is divergent, and therefore the integral from 0 to 4 is also divergent. To conclude, let's look at the integral from 0 to 1 of natural log of x divided by root x. As usual, we first need to find the discontinuities of the function, and ln of x is continuous on the positive reals, but not at 0. And similarly, 1 over root x is continuous on the positive reals, but not at 0. So neither ln of x nor 1 over root of x are continuous at 0. So we have this discontinuity at 0. And therefore, this integral is really defined as a limit, as t is approaching 0 from the right, of the integral from t to 1 of ln of x divided by root x. As t is greater than 0, ln of x over root x is in fact continuous on the interval from t to 1, and therefore we can calculate this integral from t to 1 using the fundamental theorem of calculus. Now to find an antiderivative, in this case, we're going to proceed by parts, where we differentiate u and integrate dv, which is dx over root x, in other words, x to the negative 1/2 dx. A derivative of ln of x is going to be just du is dx over x. An antiderivative of dv is going to be 2 root x. Applying the integration by parts formula, we obtain the limit of the value evaluated between t and 1 of uv, which is 2 root x ln of x, minus the integral of v du, which is 2 root x over x, in other words, 2 times 1 over root x. So we get minus 2 integral from t to 1 of dx over root x. Of course, an antiderivative of 1 over root x is 2 root x. When I multiply by negative 2, I obtain negative 4 root x, and so I'm just looking at the limit at 0 of 2 root x ln of x minus 4 root x that I'm evaluating between t and 1. When I plug in the value 1, the natural log is 0, and then I get negative 4 for negative 4 root x. When I plug in t, I'm going to get minus root t multiplied by 2 ln of t minus 4. So now I need to find the limit of this as t is approaching 0 from the right. And you see that if you multiply things through, you have negative 4, then you have negative 2 root t ln of t, and plus 4 root t. The 4 root t is going to go to 0, so what remains is really negative 4 minus 2 times the limit at 0 of root t ln of t. So we need to find this limit. And to find this limit, we can rewrite root t ln of t, which is an undetermined product because root t goes to 0 and ln of t goes to infinity, into an undetermined quotient by simply multiplying by t to the 1/2 as dividing by t to the negative 1/2. We do that, of course, because under this form we can use the rule of de L'Hopital. That means the limit at 0 of this quotient of ln of t by t to the negative 1/2 is the same as the limit at 0 from the right of the quotient of the derivatives of these two functions. So the derivative of ln of t is t to the negative 1, the derivative of t to the negative 1/2 is negative 1/2 t to the negative 3/2, and this quotient should have the same limit at 0, according to the rule of de L'Hopital. We can simplify that. We have t to the negative 1, and then at the bottom t to the negative 3/2, so that simplifies as t to the 1/2 at the top, and when we divide by negative 1/2 we are multiplying by negative 2. So in other words, here we have the limit as t is approaching 0 of negative 2 t to the 1/2. If we plug 0 in, we get 0, and therefore the limit is 0, which means that our integral is convergent and has value negative 4. Now turn to the next video, in which we're going to look into comparison for improper integrals.